name is Daniel Halpern. Today I'll be talking to you about some new stochastic fair division work. This is joint work with Gerdus and Alex, who are both in the audience. And Paritosh again, as Alex mentioned, Paritosh did have like a minor injury last week. But he very nicely made these slides. He was going to come and present. He sent them to me. It's a small evidence. But I wish he could have been here. Unfortunately, he wasn't. But big thanks to Paritosh for putting these together. Cool. All right. So fair division has been introduced multiple times so far in the session. Notice again a similar slide style to Alex. I think that's not a coincidence. Right. So we have a set of agents, a set of indivisible goods that we're trying to divide among them, and agents and goods. And here agents have some valuation function, and leave it to be a little more general. It takes in a set of goods and it gives you a number. This is how much I value this set. And the goal here will just be the fairness. Right, and so what's the fairness gold standard? Again, introduced many times, this concept of any freeness. I like my things more than your things, so I'm happy. And that's true for every pair of agents. And as this comic very nicely shows, this is really not possible, even just two agents, one good. So I guess you have Lucy and Snoopy here trying to split an apple. That actually sounds like a divisible good to me, but they couldn't figure out a nice way to split it between them. So one of them will always be unhappy, no matter what the outcome is. Right, and so there's lots of different techniques that the fair division community uses to try to get around these things and still get some notion of fairness. Right, so you can have like stochasticity, right? Like the value that people have for various items are drawn from distributions. Maybe you add money into the system, right? Like you got some item, but I got a little bit of money to compensate, so we're both happy in the end. Relaxations have been talked about a lot today, things like EF1, EFX. Or smooth analysis, another techniques, a few papers, a different flavor of randomness from the stochastic one. But today we're really going to focus on this stochastic side of things. Right, so what do people usually do? So people usually work within additive values, I say the most common model. And the most common model to get stochastic values for these additive settings, just draw the item values from some distribution. Right, and so additive means, right, you're going to draw all these values. My value for a whole set is the sum of all these individually drawn values. Again, lots of different ways you can do this. Like the original, like most standard one is you just draw these values from uniform 0, 1. Maybe we draw from some other common distribution. This Vij from Di means that each of us draws our values from our own distribution. So individually we have distinct distributions, but we're still just drawing these item values independently. And there's a lot of nice work showing that in all these settings, you get really nice, strong results. Certainly, very freeness along with other things. You don't need M to be the number of goods to be very large, like log N more than the number of agents. Really, really positive results here. So it's very different from the deterministic case. So our goal is to go beyond additive valuations. Why? Real world preferences really are pretty rarely additive. I would say, like getting more is good for you, but getting 3 things, maybe not 3 times as good. And you can come up with so many examples where it's not perfectly additive like this. But in terms of the stochastic fair division viewpoint on this, what are we going to do? I mean, what's a reasonable stochastic model to even to sample values beyond these additive ones? I also really want to hone in what is this property of the current models that are allowing for such positive results? Like they're pretty, specific on we have these additive things. So, they're really just applications of Chernoff opting bounds using standard concentration inequalities. The fact that we're letting M grow really large and we just keep sampling from the same distribution. There's something really nice and structured about these. What if we can make use of these in this beyond additive case, right? So what's a reasonable way to draw non-additive values? So there do certainly exist models for this, mainly from auctions and profit inequality. Those are the ones we're aware of. Something like here's a family of some modular functions. Pick one from it. But if this is your model for reality, this certainly is not going to help in the fair division sense. I mean, there certainly are fair division cases where EF things don't exist. Right? What if we just all like the same item? That could happen here. So I really want to say how much randomness do we have to believe exists in the real world for us to believe that every 3 things exist? Not that it's always true, but what is this property that we really need? And so really it seems to come down to some neutrality among items. We need some way in which like we like slightly different items. This is what's maybe the thing that's causing us to get positive results. So I guess what is the simplest model you could even come up with that allows for neutrality? We'll start with this. So here's our agents. Let's start even which is like completely worst case value, which any valuation function you want, like doesn't think monotone, doesn't mean anything. Like people just have values for sets of things. I don't know any structure in these things. What if you are required to be neutral? So we select a random permutation over the items for each agent, and this is your value. It's kind of like a random renamed stuff, right? Because this sounds maybe kind of strong, but like really, we're certainly doing this in like every single additive model, like all the reasonable ones you think of, like there's this independence among agents. There's like this neutrality among items, like which order you would have gotten certain values. This does already appear. So our first main result is, in some sense, is actually all you need. I think is actually pretty surprising, right? Like really, really general values. Maybe surprising, maybe not. I don't know. But we'll get to how you prove this after, and maybe that'll convince you. But no matter what valuation function you start with, you have two agents. You do need an even number of items. You have an odd number, it's very easy to construct counterexamples again. But really, in this case, the neutrality is somehow all you need. If you do some random relabeling, there will be memory-free solutions. Something that's growing extremely close to 1. Right, so this even m is necessary. This probability bound is tied up to constants. That's what I meant by the star. Even for additive value. So the hard case is just we all like the same item. And I think the kind of cool thing, maybe a little new to pair division, is how we prove it, which I'll get to a little later. And it has something to do with some like hypergraph automorphisms, which I thought was very surprising when we started working on this. So I'll talk about that more after. Really quick, our second main result. I think the slides have a little be boxed around that. A different class of valuations. I won't talk about this so much. Order consistent ones. This is values where you have there's a natural order over them. You sort of have a favorite, and a second favorite, and a third favorite item. Not necessarily any extra things about this, but when you're comparing two bundles, there's a notion of like SD preferring, stochastically dominated preferring. So it's a very natural generalization to ordinal pair division. So sort of no matter what your underlying values are, you will prefer things that sort of have higher rank. So it actually is very strong. The ordinal thing, I won't talk too much about this. The slides seem to have gotten all messed up. There it is. Yeah, so like the classic round robin can work, and this does capture lots of known valuation settings. So things like unit demand, single-minded, budget additive, they all fall under these order consistent valuations. Okay, so here in this place, we're gonna have this setting. We're gonna have as long as m is at least n squared. We're good. But I'm not gonna and this is tight if you have fewer than n squared items. Free allocations won't exist. But I want to come back to the two agent, this hypergraph setting. So I think this is pretty cool technical result. The two agents are arbitrary values. How are we going to think about this? So first of all, what's a hypergraph? Just a graph with a set of vertices. Instead of edges just being between two vertices, they're arbitrary sets. Just think of like it's vertices and a bunch of sets on top of these vertices. We're only going to consider allocations that exactly divide the bundles into two. This is in some sense without lots of generality, because you can define value functions that need this to be the case if they were unbalanced. It would for sure not be memory free. And in this case, we really can represent value functions by we call it m/2 uniform hypergraphs, just by sets of size m/2 placed in this graph. So the nodes here are items, and I'll say a set is in the graph if I prefer it to its complement. Right, so let me just give an example. Here's some values you could have over sets of size 2 of 4 items. So I like this is an agent that just always likes item 1. Right, so if between any two bundles, we'll pick the one with item 1 in it. We can represent this by this graph here. So there's 3 possible partitions, and I like the set of 2 better than its complement as long as 1 is in it. And the idea is that this like random relabeling step that we had in our stochastic model really just corresponds to permuting the vertices in this graph. Right. So this certainly corresponds to value function. When we apply the random model, we get rid of the vertices. This is a new valuation function. And as for some terminology, if you haven't seen this from some abstract algebra, and permutation is an automorphism if it just brings you right back to yourself. Right. So for example, if I swap 2 and 3 here, this graph is actually the same graph in terms of what things are in some set. That would be an automorphism. If I also swapped 1 and 4, this is now in some sense a different graph, right? Like 1 used to be in 3 sets with lots of other things. Now 1 is just in one of these sets. Okay, so this is like a nice way to represent value functions. What else can we do with this? So let's say we have 2 agents with these values represented by 2 hypergraphs. The key observation is that every free allocations exist if these 2 hypergraphs are not identical. Why is this the case? This means that there are 2 sets, a set and its complement, where I like one of them and you like the other. And that's our perfect Henry free allocation. You like one, right? In fact, Henry free allocations will not exist only if we apply this random relabeling, we do this random computation, and we end up with exactly the same. Right. So in terms of a counting thing, you could show that the probability that no Henry free allocation exists exactly proportional to the number of permutations that are automorphisms that map a graph to itself. Like, okay, this is like a nice observation. We should just go to the combinatorics literature and cite something and find something else. This didn't exist. We couldn't find it. And it was a decent amount of work, but we proved like a bound on just the general number of automorphisms that a hypergraph with sets of size k can have. Turns out it's at most this, and this is reasonably close to text. I think like m factorial over m. Some of it is a lower bound, right? And so once you have this big results on hypergraph, you sort of plug it into the observation before about Henry freeness and how we're representing these value functions, and you can show that the probability that no Henry free allocation exists is 1 over n up to it. All right, so just to wrap up a little bit, and we define a new stochastic model just to understand, to draw values from a general valuation class beyond additive. We show that with 2 agents, it doesn't matter any arbitrary evaluation structure in them. Henry-free allocation exists with high probability. And some corresponding results for order consistent valuations, which encompasses a broad class of beyond additive things. But in terms of open questions, our biggest thing is this thing only works for n equals 2. It seems to beyond n equals 2, it starts getting very complicated, like working with different distributions or like different permutations at the same time. But our conjecture is that these really should exist with high probability for all n. And it's a really big open problem. And the thing is, what are other reasonable models of stochastic beyond additive pair division? And I think this is nice when they captured like some property of the existing additive ones and let us generalize, let us work with them. But unclear like what the perfect one is for different situations in the real world. And certainly, I think a nice idea is just coming up with like the right stochastic model for various settings and seeing what we can get there. So that's all I have for you. Thank you.
For n equals 3 and higher, does this also reduce to some sort of automorphism counting problem, or is it totally different?
A much bigger generalization of it. So with n equals 2, it's nice because you can say like one agent is basically fixed, and I'm only sampling one thing. I think there is a way to define a broader generalization, but it gets much harder because like checking the Henry free condition, now it depends not only on what I get, but sort of how your things were split among the other 2 people. So I think there is a way to define it, but it's not as easy for problem. Any other questions?
So I didn't get how the split to these same size splits is the general case. Maybe I missed how that implies the general case.
Assuming the number of items is even, we're showing that we are able to find an free thing that is balanced. So it was an extra assumption that we were only going to look at balanced things and show MU-free solutions exist for balance. It is not hard to show that like, that's basically without loss of generality. If you have a value function, I can modify it into another one where basically, unless your balance will for sure be unhappy, we may as well only look at balanced allocations.